Hi again everyone, Chris Tisdell here again. In this presentation, I'm going to continue my series of videos that give a gentle introduction to complex numbers. Now in previous videos, we talked about the basic operations with complex numbers and the geometry and how to add, subtract, multiply and divide. I also showed you how to solve quadratic equations using the quadratic formula when complex numbers are the solutions. In this presentation, I'm going to go a little bit further and talk about the complex conjugate of a complex number. So let me share my screen with you and we can get underway. Okay, so before we actually get down to it, let me just remind you of a couple of examples, right? The complex conjugate. This, from a previous video, when we were dividing one complex number by another, we looked at the denominator and we changed the sign of the coefficient of I and we multiplied through by a factor of 1. That put this form into the Cartesian form, which simplified it. Now, this 3 plus I and this 3 minus I, they're the conjugate of each other. Okay? In the previous video, we solved a quadratic equation and we got two solutions. And you can see the signs differ on this coefficient of I, and the real parts are the same. These two are conjugates of each other. So for this solution, this is the conjugate, and for this solution, this is the conjugate of that. So we've already seen two important applications of what's known as the conjugate. So we're going to look at this idea a bit further in this presentation. Okay, so division and solutions to quadratic equations and polynomial equations. Okay, so suppose I have a complex number z written in Cartesian form, x plus yi, where x and y are real numbers. X is the real part, y is the imaginary part. Then we talk about the complex conjugate of z as this z bar, and basically you have the same real part and you just change the sign on the imaginary part. Okay, so let's look at a couple of examples. If you had 3 plus I, the conjugate of 3 plus I is 3 minus I. If you had 1 minus 2i, then the conjugate of that, you just change the sign on the minus 2i. The conjugate is 1 plus 2i. And let's say you had negative 1 minus I, the conjugate of that, change the sign on the negative I. The conjugate of that would be negative 1 plus I. Now the conjugate has an easy and simple explanation using geometry. Suppose I'm working in the complex plane here, and let's say this is my complex number z, that's where it's situated. To get to the conjugate, you just reflect in the horizontal real axis. So that'd be your z bar. Okay. So that's the kind of relationship between them using geometry. Okay, so let's look at a few properties of the conjugate, and I'll do a simple example in a minute. Suppose I have, say, a complex number z and a complex number w. Then I'm going to just give you a list of some of the basic properties, kind of like a reference list if you like. Okay, firstly, if I multiply a complex number with its conjugate, then I always get a real and non-negative number. Okay, and it turns out that this is going to be equal to the square of the distance from z to the origin. I haven't talked about, lengths and distances and a modulus yet. I'll do that in upcoming videos, but just for future reference, this is actually the square of the distance from the point z to the origin. So z times z bar is always a real number and it's a square of a distance. Secondly, if I take the conjugate of a conjugate, I get back to where I started. So for example, if you start here, oh, hang on, my screen's just frozen. Let me fix that up. Okay, there we go. Okay, secondly, the conjugate of a conjugate is the original complex number. So why is that true? Well, if I'm here and I take the conjugate, I flip down there. And if I take the conjugate of that, I flip or reflect back up there. So I'm back where I started. Okay. All right. If I want to take the conjugate of a sum, it's just the sum of the conjugates. Same with the difference. If I take the conjugate of a difference, it's the difference of the conjugates. The conjugate of a product is the product of the conjugates. And there's a similar one for division. There's also a power rule. If I have a complex number to a power and I take the conjugate of the whole thing, then it's the same as taking the conjugate of z and then raising it to the power. Now, two very important aspects and identities are the following, and we'll use these a lot. If I take the complex number z and I add its conjugate and I divide by 2, I just end up with the real part of z, or just the value of a. Some books write this with re. Okay, and on a similar tip, if I have a complex number and I take away its conjugate and divide by 2, then I just get the imaginary part of z. Some people write this im for imaginary. Okay, so let me actually prove one of these. I won't prove them all. I'll leave them as a sort of exercise for you to do, but let's just prove this. I mean, a lot of these are kind of obvious, and you can actually work them out geometrically, like that one, and a few others. So let me start with this, and we'll see if we can, actually prove this. And the way I'm going to do it is just look at this form and write down this form, add them together, and add by 2, and divide by 2. Okay, so it's going to be a plus bi plus the conjugate. So if that's my complex number, the conjugate will be a minus bi. And I want to divide the whole thing by 2. Okay, so if I add the like terms, so a and a is 2a, bi minus bi, that will disappear. So the 2's will cancel, and that just leaves us with a, which is the real part of z. So that's a very quick proof. So try proving the other results if you can. Okay. All right, let's look at a simple example. Okay, now we'll use these in various examples, and this as well, and this as well. So I'm going to do some more detailed examples in other presentations, the kind of examples that kind of deserve their own presentation because they're quite potentially heavy. But here are some real basic ones. Okay, here I've got a complex number z, and I'm asked to calculate and plot the following expression, z bar and z plus z bar. Okay, well, this is a really easy example because we can actually sort of work out where we want to be without doing any calculations whatsoever. Okay, so if that's z, I know the z bar, I just change the sign on that 3i to negative 3i. And geometrically, if I plot that, then I just would reflect that point in the horizontal axis to get that. What about z plus z bar? Well, we can use this thing down here. Z plus z bar is going to be 2 times the real part of z. The real part of z here is negative 2, so 2 times negative 2 is negative 4. So I know that that will be negative 4. But let's go through and actually work it out, and then we can plot them. Okay, so let's go with part A. So if z is negative 2 plus 3i, then z bar, the conjugate, is negative 2 minus 3i. Okay, that's pretty easy. And part B, z plus z bar, that's going to be negative 2 plus 3i plus negative 2 minus 3i. So, the 3i's will cancel and you'll be left with negative 4 as expected. Okay, so let's plot everything on an argon diagram. Sometimes, I mean, I use the complex plane. Sometimes people use the term argon diagram. Okay, so let's just draw in I want to plot that, that, and that. Okay. Okay, so I've got my real and imaginary axes. I've got, say, 3i up here, negative 3i down there, and say negative 4 there. So let's see if we can draw in our complex numbers. So for z, I want to go 2 units this way and 3 units up. So it'll be somewhere like that. So that'll be z. And to get z bar, I just would reflect that in the horizontal axis. It's the same as going 2 units to the left and 3 units down. And lastly, z plus z bar, well, that's real, so it will lie on this horizontal axis, and we go 4 units to the left. Okay, so let me just label them, and we'll be done. Okay. Okay. All right, so there you have it. I've told you about the conjugate, given you some geometric interpretation and how to calculate it and some of its properties. If you want to, you can try to prove some of the properties in that reference list that I gave you. And in forthcoming videos, I'll do some deeper examples, some more involved examples where we're using properties of the conjugate. So a little bit more advanced than the simple example that I talked about today. So if you have any comments, any questions, I'd love to hear them. You can put them in the comment section below. If you have any suggestions, you want me to look at certain kinds of areas of maths, I'd love to hear from you. So thanks for watching, and please join me for the forthcoming presentations where I'll do some more detailed examples on the conjugate. All right, see you later.